So in this particular free fall problem, or vertical kinematics, we have an object that's being shot straight upward with an initial speed of 24.5 meters per second from a height of 120 meters above the floor. So here in the diagram, it shows floor on the bottom, and the object is currently 120 meters above the floor, which is our reference point, and it's being shot from that location at a speed of 24.5 meters per second. So if you want, pause all these different parts, or pause the video and write down all these different parts, and keep up with the diagram, okay? Otherwise, you'll get lost with what I'm doing. All right, let's do it. Part A asks you to find the height that it reaches relative to the initial launch positions. So again, in the diagram, the launch position is at 120 meters above the floor already, but it says relative to the initial launch position. So it just wants it relative to where this particular starting point is. All right, so to do this, I like to point out that it's important to keep track of this particular quantity. Acceleration due to gravity, which is always directed downward the page, is negative 9.8 meters per second square. Here I have it, you notice a y, or acceleration in the y direction, which is commonly accepted as acceleration due to gravity, which is shorthand g, and the value is negative 9.8 meters per second square, and this exists 24/7. It exists all the time, whether an object is being shot upward, whether an object is being thrown downward. Okay, so keep those concepts in mind as you practice this problem. All right, let's do part A. Calculate the maximum height, right, hmax, that it reaches relative to the initial launch position. So I think the easiest way to knock this one out is using this particular kinematics equation. I'm using this because I know at some point that the object here that's being shot upward will eventually slow down and come to a stop and then turn around and fall down. So I want to use this. Why? Because I can cross VF out. I know VF at some point is 0 because this particular statement asks for hmax. Hmax implies that the object is no longer rising. It has to come to a momentarily stop and then fall back down. So in this case, I'm going to use this function because VF I can cross out, which just simplifies down to just negative VI squared equals 2G delta Y. And then therefore I can just plug values in. VI here being 24.5 meters per second, which I substituted in. I carry the square down. The negative sign in front of the term gets carried down. And then the 2 gets carried down. G, I substitute in for negative 9.8 meters per second square. And here the only unknown is my variable delta Y. So to solve for delta Y, I can just simplify my work. 2 times negative 9.8 is just negative 19.6. And then to solve for delta Y, you would have to divide both sides by negative 19.6 algebraically. And then to do so, as you can see, the negative signs will cancel out. And just make sure you don't forget to square the 24.5. So 24.5 square, and then divide that by 19.6. That'll give you an answer of 30.625 meters. Now, I want to point out that you need to keep track of this value. So write it down if you're watching and keeping along, because I will be using this value in later parts. So when I reference it, you already have it to go. Okay. So according to the diagram, it suggests that the object will rise a distance of 30.625 meters before it actually turns around relative to where it was launched. So watch my cursor. It's going to rise, slow down, eventually come to a stop. So by the time it stops, it has risen a distance of 30.625 meters. Okay. All right, let's do this slightly different. Now, if you wanted to use the displacement function to find delta Y, which is fine, you can find delta Y is equal to VIT plus 1/2 GT squared. Now, if you plug in VI being positive 24.5 because it's being projected upward, you notice here the only variable you don't have in the statement is T, right? You don't know what T is. You know what G is. It's negative 9.8, but you don't know what T is because here I have a T, and on the right side I have a T squared term. But that's okay, which is so it's perfectly okay to run into a variable that you don't know. But hopefully, as you're practicing and you're thinking about this stuff, well, I can use the average acceleration equation to find T. Here, A is just G, again, because acceleration due to gravity is just negative 9.8, which we know. So the only thing I don't have is actually my T. Well, to solve for T, I need to move the delta T up to the left side, and I'll move the A down to the right side. So I'll do a little algebra manipulation there. To do so, we can expand delta V equal to VF minus VI, and then over A. Here, I know what VF is. I'm going to reference the peak of the flight, which will cause VF to equal to 0. Okay, so that's important. I want to find the time that it takes for it to come to a complete stop. If it comes to a complete stop, VF is 0 minus VI, but VI is positive 24.5. meters per second, as you see in the numerator there. And then A is just negative 9.8. So I can just simplify this, 24.5 divided by 9.8, which will give me an answer of 2.5 seconds. Well, now that I know how much time it takes for the object to come to a complete stop, I can plug it in for my delta y function, which I don't know what t is, okay? However, before we do that though, I do like to encourage common sense, okay? If you watch these arrows that comes up, if the initial speed is 24.5, every second that goes by, your velocity decreases or slows down by 9.8 because acceleration due to gravity causes an object to slow down as it rises, but then speeds up as it comes down. So in this case, using common sense, this 24.5 meters per second will change by a value of 9.8. So therefore, 24.5 minus 9.8 will give me 14.7. But then another second goes by, I can just subtract another 9.8. So 14.7 minus 9.8 will give me a value of 4.9. So at 2 seconds on the way up, it's moving at a rate of 4.9, which makes sense because it's slowing down. But then notice here, 4.9 is half of 9.8. So therefore, it would actually only take another half a second to slow down to a complete stop. Okay, so that reasoning skill I think is important. So if you think about it, drawing these arrows super easy to do. Whatever the initial velocity is, just subtract it by 9.8 every second, and then find how much time it takes to come to a complete stop. For this one, at 2 seconds, it's 4.9. So 4.9 again is half of 9.8. Hence, it only takes an additional 0.5 second to bring the object to come to a complete stop before it changes direction. So you notice here using common sense reflects what we get here using kinematics equation, which is 2.5 seconds. Once you do that though, just carry the displacement function down. So here I highlighted in yellow for you. All I did was I substituted t for 2.5 seconds, and then I carried the t squared term down, so 2.5 seconds square. And if you simplify all this, you'll get the first term is 61.25 meters, and then the second term, because it's 1/2 times negative 9.8 times 2.5 square, that negative sign is going to cost you quantity to be negative here. So therefore 61.25 plus a negative value of 30.625 will give you a positive 30.625. So as you can see, the answer here is the same as the answer on the left side. So pick one that you would like to do. I like the left one because I don't have to go find time, okay? All right, so let's do it. Let's do part B. Part B asks you to calculate this average speed during the time interval from 0 to 2.5. Well, for this one, it's important that you kept track of what I just did in part A, okay? So to find average speed is still equal to distance over time. Here, the time is 3.5 seconds because the problem starts at 0 and it ends at 3.5 seconds. So my time is given to me. I don't know what the distance is though, but that's okay. I can go find the distance real quick. I already know that the distance going up is 30.625 meters, which I hope you kept track of. If not, pause the video and rewind it real quick. And that time was 2.5 seconds, okay? So according to this diagram, it took the object 2.5 seconds to rise before it changed direction. But for part B, it wants the average speed between 0 to 3.5. Well, I already know that it took 2.5 seconds to come to a complete stop, but this time interval is 3.5. So I know it's going to have to fall one more second to meet this condition in part B, right? Because it's just from 0 to 3.5. Rising only takes 2.5 seconds, so therefore it's going to have to fall another second. 2.5 plus 1 equals 3.5. So here, I've chosen to use my displacement function, but I can cross VI out because I'm going to start at the very, very top where it stops, and then on the way down, it falls for an additional 1 second, okay? Therefore, I can just replace my kinematics function with 1/2. G is negative 9.8, but the time here is 1 second. That's important if I just lost you there. It took 2.5 seconds to rise, but the problem wants it from 0 to 3.5. So it's going to take an additional second, but now it's on its way down. But starting at the peak of the flight suggests that it starts at 0 meters per second because it came to a stop momentarily. Okay, so therefore I can cross VI out. So if you do this correctly, the distance that it falls during the last second from 2.5 to 3.5 seconds would just be 4.9 meters. Even though I solve for displacement here, I need the distance, so I can just do the absolute value of negative 4.9, which is just 4.9. So the total distance would be, ready, 30.625, because that's how much it rose before it came to a complete stop, which only took 2.5 seconds. And then from 2.5 to 3.5 seconds, which is a window of 1 second, it has fallen a distance of 4.9. So here I need distance, which is a scalar quantity. So everything here, as you can see, is a positive value. So during the time of 0 to 3.5 seconds, it has traveled this much distance in the numerator, 30.625 plus 4.9. So if you simplify that in your calculator, you should get an average speed of 10.15 meters per second. Okay, and speed is a scalar, so you don't need to add any direction. All right, let's do part C. Part C asks you to find the average velocity for the first 5 seconds, which is pretty easy to do. Well, to find average velocity, we need displacement over time. All right, so we know our time already is 5 seconds because that's given in the statement, but we don't know what our delta y is. Well, to find delta y, really is just VIT plus 1/2 GT squared. My VI here is 24.5 because it says the first 5 seconds, so I want to start at 0 second, but at 0 second, the object's being shot up at 24.5 meters per second. My time here is 5 because the interval is for the first 5 seconds. G is given, it's negative 9.8, time is 5, don't forget to square that. And then if you do all this, you should get 1.225 plus a negative 1.225. So the same positive value plus the same negative value, which equals 0. So therefore, the displacement is 0. So therefore, the average velocity is just 0 meters divided by 5 seconds, which is 0, which to me makes sense. Now, here's why it makes sense conceptually. Well, the object starts here where my cursor is kind of, going back and circling here. It took 2.5 seconds to rise. Therefore, it also took 2.5 seconds to fall. Well, 2.5 seconds up, 2.5 seconds down, that's a total of 5 seconds. But at exactly 5 seconds, I'm back to where I was. So really, even though I travel upward and I travel downward, my displacement is 0 because my position hasn't changed. I'm back to where I started. So therefore, displacement is 0. And if displacement is 0, it doesn't really matter because any time interval on the bottom it doesn't affect the outcome. So 0 divided by any time quantity will give you 0 meters per second. So that's just a reasoning skill. Okay. All right, let's do part D. Part D asks you to calculate the total distance traveled. Now this one's a little tricky. This one we just have to do a little thinking. Okay. To find the total distance, well, we found in part A that it rose a distance of 30.625 meters before it came to a stop, and then it starts to fall down. So therefore, to find the total distance, watch my work. The total distance is the distance up plus the distance down to where it was launched plus the 120 because it was initially 120 meters above the ground. So watch these arrows. This green arrow, if you've been keeping up my work, that is a length of 30.625. That's how far it traveled upward before it came to a stop. So therefore, that's the distance. Now coming down though would also be 36.25 meters because of symmetry. So you've gone 30 meters about, and then another 30 meters down, and then you still have to fall this additional 120. Hence, in my work, I'd have D up, which is 30.625. I have D down to where it was launched, which is another 30.625 plus the extra 120. Okay, so therefore the distance that it traveled from start to finish is 181.25 meters. Okay, so if I just lost you there with these two arrows, think about it. Due to symmetry, distance up must equal distance down, but don't forget to add 120 because the finish is on the floor, not where you started. All right, let's do it. Part E, find the total time of flight. To find the total time of flight, I think the easiest way to do it is use the displacement function. Okay, here my delta y is negative 120. I know that the object got shot up and then it turned around and it came down, but in this particular function, your delta y is independent of the path taken. All that it cares about is where did you start and where did you finish at. So if you watch my cursor, the ball's here. Yeah, I know it traveled up and I know it came down, but all that I care is where did it start, which is here, and where did it end on the floor. So if my cursor, if you follow my cursor, it starts here and then it finished on the floor. Well, if you watch my cursor, the cursor that I just moved travel a distance of 120 but it moved downward, so therefore my displacement is negative 120 meters. Okay, so therefore that's why my delta y is negative 120. So it's important that you have this negative sign, otherwise what I'm about to do will jack your answer over. Okay, so here delta y is negative 120 because it fell downward from where it started. My vi is positive 24.5, and then 1/2 negative 9.8, and then times t squared. But here I notice that I need quadratic because I have a t square, I have a t, and then I have a coefficient. So therefore, in order to solve for t in this particular format, I need to set the whole entire function equal to 0. So this negative 120, I want to move it to the right side, which makes it positive 120. But then you notice here, I just like to rearrange it so it looks like quadratic. My t square, and then I have a t here. In math, we like to write the variable with the highest exponent first. So in this case, t squared is highest, and then it goes to t, and then it goes to the number without the t. So therefore, 1/2 times negative 9.8 is just negative 4.9 t squared. And then the 24.5 t, I just moved to the second term because I'm just rearranging the order from highest exponent to lowest exponent. And then the 120 remains positive 120. But here, I notice that I can use quadratic because it has that format of ax squared plus bx plus c. So here my a is negative 4.9, my b is a positive 24.5, and then my c for this problem is a positive 120. So what I'm going to do is I'm just going to exit my screen here and just use quadratic. So if you're keeping up right now, I'm just going to go with this. I'm just going to use quadratic. So my A is negative 4.9, my B was 24.5, and my C was 120. And if I hit calculate on this particular calculator online, it gives me a value of 8.04. Again, I don't care for the negative value because here I'm solving for time, and time cannot be negative. So really it tells me the total time is about 8 seconds. Okay, so 8.04 if you want to be all technical. All right, so let me go back to my stuff here. Okay. So as you can see, if you follow that particular strategy, which I like, assuming your calculator allows you to do so. So if you have one of those, I call it wimpy calculators, the little scientific calculators, it will not do quadratic for you. Okay, so if you have a graphing calculator, this should be done fairly quickly. So the time here, as you can see, is 8.04. Now, if you don't like using quadratic because it either scares you or intimidates you, then you can chunk it up. Okay, well, here in my work, I'm still in part E. I can find the time that it takes to travel upward, which is 2.5 seconds. Again, from either using these arrows or just doing algebra here. Here I have T up equals VF minus VI over A. At the peak, VF is 0, so I'm just going to cancel that out, or you can plug in 0 if you want. Minus VI, VI being 24.5, A being negative 9.8. So if you simplify that, you get a time of 2.5 seconds. But that's just the time to go upward. Now I need to find the time to go all the way to the bottom. Okay, so it's gonna rise a distance of 30.625. It comes to a stop, and it's gonna fall all the way back down. Well, I know that it takes 2.5 seconds to go up. I just need to find the time that it takes to fall all the way back down to the floor. So to do that, I can use my displacement function. I can use this to find the second half of the problem where it falls downward. Well, if I start at the very peak, my VI is 0. But if I start at the peak, my displacement that the ball will fall is negative 150.625 because, well, it's all the way up here. Watch my cursor. It's all the way up here. That's where it came to a stop. It's going to fall back to where it was, which is a distance of 30.625. And then it's going to keep falling an additional 120. So 30.625 plus 120 is indeed 150.625. And again, it's negative here because I'm starting at the very peak and it fell down to the floor. So therefore the movement is in the negative direction. It fell down. My VI is 0 because I'm starting at the peak because it starts at 0 because on the way down its initial velocity is 0. And then I can just plug and chuck. Okay, 1/2 times negative 9.8 is negative 4.9. To solve for t squared, divide both sides by negative 4.9. And then you get 150 or negative 150.625 divided by negative 4.9. The negative sign cancels out, and then you got 150.625 divided by 4.9, which gives you 30.74 about. And then to solve for t though, we need to square root both sides because this is t squared, so therefore to solve for t, radical both sides. So if you radical 30.74, you should get a time of 5.54 seconds. Now, well, this is not your answer though, right? it asks for the total time. So all you have to do is, again, think a little bit. It took 2.5 seconds for it to rise to the peak, but from the peak, it would take an additional 5.54 seconds to fall down to the floor. So the total time would be 2.5 seconds, which is the time that it took to get to Ymax. But then from Ymax all the way to the floor would take an additional 5.54 seconds. Therefore, the answer is 8.04, which is very consistent with what I have here on the left side of my work. I like using quadratic, but if you don't have a graphing calculator that can do this for you, you're going to end up doing, busy work doing quadratic by hand, which I don't encourage because that's just a waste of time. So get a calculator that works. All right, part F. It says an object is shot straight up. Part F asks you what is the object's velocity just before it strikes the ground. The easiest way to do this one, I think, is just using this particular function again that does not involve time. Okay. All right. Therefore, I know everything. I know my VI. I know my delta Y. So to solve for VF, I need to move this negative VI squared to the right side, which change the sign. So it went from negative VI squared to positive VI squared. Here, I just plug and chug. G is negative 9.8. Delta Y is negative 120 because, again, it starts up here. Even though it went up and all that, I don't really care. All I care is that where did it start? Where did it end? It started at 120. It dropped down to 0. So therefore, my displacement is negative 120 because it fell downward. And then VI is given as positive 24.5. I'm going to square that. So if you do all that, 2 times negative 9.8 times negative 120 makes it a positive value because a negative times a negative is a positive. So you get 2,352. And then 24.5 square will give you 600.25. And then both these values are positive, so we add that, we get a bigger number. So therefore, VF squared is equal to 2952.25. We'll have to find VF, which is square root both sides. Now, I want to point out though, when you square root, you get two answers. You get a positive and a negative answer. So keep that in mind. So notice here in my notation, I have a positive and a negative value. Now, which answer would you pick? I would go with the negative one because, well, it's falling as it strikes the floor. So therefore, I want to pick a value that's negative. So my answer is negative 54.33 meters per second. Okay, I don't know why there's a square there. Excuse me. Hold on, let me fix this real quick. Sorry, when I took the square root and I didn't. Okay, that should just be meters per second. All right, so let's do it. Okay. All right, that's. Ooh, hold on. Sorry. Notice this should be meters square. All right. Sorry, because on the top here it says meter square plus meter square, so that should be meter square. Excuse me for my error there. I just fixed that. Okay. Again, but if your units are on the proper units, when you do your scratch work, you don't have to write units out. I just like to write units so that you see where everything comes from. All right. So let's go ahead and knock out part F using a different strategy. Part F, to find part F, the V just before it strikes the ground. You can also use this kinematics equation. The final velocity is equal to acceleration times time plus VI. But here, I want to start at the very, very top. Okay, again, it's going to rise and then it's going to fall. So I want to start my problem at the very top because in the previous part, I just found that the time for it to fall from the peak all the way to the floor is 5.54 seconds. So if you need to rewind the video and watch that part again, I found the time from the very, very top to the very bottom floor is 5.54 seconds. So therefore, I can just plug in G, which is negative 9.8. I know the time that it took for it to fall from the peak all the way to the floor is 5.54 seconds. So all I have to do is just multiply, and therefore I'll get a value of negative 54.29 meters per second. Now, I don't know about you, but negative 54.33 and negative 54.29 is pretty much the same. Give, take, due to rounding here. All right. So let's do part G. All right. Part G is a little tricky. This one I think is the hardest one out of the parts. It asks you for what is the average velocity between 100 meters and 40 meters relative to the floor. So here on the right, I have it kind of just not drawn a scale. I'm just giving you a visual. So here's the 40 meter mark because the floor is 0. So you're going to go up to 40, 50, 60, 70, 80, 90, 100, 110, 120, whatever the case is. All right, so 40 and 100. So it wants to find the average velocity during this time. Well, it's going to be falling down by the time it hit 100 and by the time it hits 40. So let's do it. To find average velocity, we need two quantities. We need final velocity and initial. Okay. but I don't know how fast these things are moving by the time it falls down and reaches a position of 100. And it's going to keep falling down until it hits the 40 mark, until it hits 0. But I can find these values fairly quickly. Well, I can use this kinematics equation. Why? Because I can start the very, very peak of the problem. If I start the very, very peak of the problem, I can, cross out certain things. Okay, so let's do it. So all I'm going to do is I'm going to apply this function twice. Okay, to solve for VF, I just need to move the negative VI squared to the right side. So you notice here in these two lines on the bottom, the VI squared term is on the right side of the equation, and it changes sign. It went from negative to positive. Well, I'm just going to plug values in. Here, I have 2, and then I have G is negative 9.8, and then delta Y here is negative 20. It's negative 20 because I'm starting from the position where it started, and then it fell down to 100. So that would be a difference of 20, and it's negative because it's falling down. Okay, my VI is given as 24.5. I want to square that, and then if you do all your calculator work carefully, you should get a value of negative 31.5. I want to remind you, when you take the square root of a number, you get 2 answers. Here, I've chosen to go with the negative answer because, well, it starts at 120, and I need to know how fast is it moving at 100 meters, which means it's on its way down. Because it's on its way down, I want to use the negative value here. Okay, and I can use the same strategy to do the right side here. It starts at 120, but I need to know. I know it went up and down. Okay, but I don't really care. I'm just going to start from where it started, and then I'm just going to go all the way down to 40. So therefore, I use the same equation. Okay, and now all I have to do is plug in G, which is negative 9.8, but delta Y here is negative 80 because the starting point is 120. You're going to fall down to where it's 40, so you've only fallen 80. Okay, because 40 plus 80 makes 120. So that's how you think about this stuff. Okay. So you put your cursor there, which is at 120. It fell down. It keeps falling. It keeps falling. So by the time it gets to the 40 meter mark, we would say that the object has only fallen 80 meters. Well, displacement is a vector, so I need to put in a negative sign. My VI is still the same because it's being shot upward. But again, displacement is independent of the path taken. So all I care about is the starting point and the ending point. All right. So if you're keeping up, watch my arrow that came up. Again, you notice I'm measuring from the starting point to where it ended. So that length of the arrow is 80, but I'm using negative because I need displacement. So therefore, if you finish your calculator work, you should get a value of negative 46.56. Okay. Again, when you square rooting this value will give you a positive and negative. We want to use the negative value because it's on its way down. So here we just found VF and VI. Okay, I know even though both these works as VF, but these are VFs at different locations. So I know the final and the initial velocity, so therefore I can just plug values in. I know my final is negative 46.56. I know my initial here is negative, 31.5. Whichever you want to call VI and VF doesn't really matter because you're just adding these two values anyways. So you have a negative plus a negative, so whether you put the 31.5 first or the 46.56 first, it doesn't really matter. You're still going to get the same sum in the numerator. All right, so if you add all that, I think I'm missing a decimal here. Yeah, excuse me. This is massive. You notice there's a lot of, all right, I think the decimal place goes right there, okay? All right. Okay. All right, so therefore, if we do that, we can just divide the negative 78.06 divided by 2. So we get a value of negative 39.03. That would be our average velocity using this particular strategy. Now, if you don't like doing the strategy, you can do the average velocity is equal to displacement over time. Here, I know my displacement is negative 60. Okay, that's because, well, if you start at 100 and you end at 40, you've only gone, down 60 meters. So I know my displacement is negative 60. Okay. So if I just lost you there with the negative 60, think about it. The balance here given is 100 meters and 40. So to go from 100 to 40, you've fallen down 60 meters, so which is negative 60. I don't know what my time is, but that's okay. To find my time, I can use this particular displacement function, and I can find the time. If I can use the very, very peak of the flight, okay, so the ball's going to rise momentarily, come to a stop, and that's where my initial starting point here is. if I want to use the peak of the flight as my starting point, which means that it came to a stop. Because it came to a stop, my VI is 0. So therefore, my displacement function is simply reduced down to just 1/2 gt squared. And I want to use this twice, just like the last strategy, except here, my displacement here is negative 50.625. So if you could keep up with the work here, yeah, it's negative 0.625 because we know that it rose 30.625 meters, and then from that distance down, which is another 36.25, but then this puts you at 120, but then you got to go down to 100, which is an additional 20. So really 30.625 plus 20 gives you negative 50.625, and then here it just becomes calculator work. So therefore, if you simplify all this, again, 1/2 times negative 9.8 is negative 4.9. Then to get t squared by itself, divide both sides by negative 4.9, which leaves you with 10.33. And then to solve for t, radical both sides, and then the radical of 10.33 gives you a value of 3.21 seconds. So again, I'm starting at the very peak. It fell down 30.625, but to get to 100, it's going to fall an additional 20, which is negative 50.625. And I want to use the same strategy on this right side. The negative 110.625 comes from, watch my cursor, it's going to fall down 30.625. It's going to go all the way down to 40, okay? But from 120 to 40 is a difference of 80. So therefore 80 plus 30.625 is negative 110.625. Okay, I hope you've been keeping track like I suggested from the get-go. Okay, therefore all this is now is just calculator work. So I simplify the right side down to negative 4.9 again, and then to get t squared by itself, divide both sides by negative 4.9. That will give you a value of 20.58, but this is t squared. Now to get t by itself, we radical both sides, so the square root of 20.58 is just 4.75 seconds. Now the question is, what do you do with this time? Okay, well, you have to take the difference in this time. So to fall from 100 meters to 40 would only be 1.54 seconds. Okay, so you have to take these two times and subtract it. So therefore, I know my delta t now is 1.54, and so if I do that, I should get a negative value of 38.96, which is practically the same answer as we got in the previous strategy. So think about it. Hopefully pick a strategy that works best for you. As I stated earlier, this is the hardest part of the problem. All right, I hope that makes sense. Stay nerdy, don't be whack.